button. All right, we are now recording. I would like to point out for everyone that we are recording. Just if you don't want to be recorded, make sure to keep your microphone and webcam off. We will put this on YouTube later, hence the need to record. So there's that. I'll wait for a couple more minutes and then we'll get started at like 5:05. And in the meantime, I'd like to ask everyone, how's your week free going? Is it going well? Is it going bad? Any, I don't know, funny assignments, if you will, or, you know, anything interesting happen? For chicken codes. Well, you will get my chicken code later. How's my 123 project Mate? Well, it worked well. They kind of pulled a fast one on us by putting something in the tester that was not in the specification, and pretty much nobody got a full score with the exception of very few people, like 5 people or something. It worked out well in the end, sort of. Nishant said, I'm in lab right now. Steven said he's in lecture right now. Well, supposed to be in lecture. I mean, to be honest, you dismissed one lecture to come to another. So hopefully you'll enjoy this one better when we eventually get started. Welcome, Jason. We'll wait for a couple more minutes and then we'll get started. Have some water. It's actually really cold in the apartment. It's weird. Double zoom is like multi-track drifting. Well, Nishan, you're kind of right, but really the best one is when you're double like zooming on 2 different like devices, but not like the computer, right? Like the laptop in your phone or something, and you're like in the kitchen doing stuff. And the best part about that is just how heated everything becomes and how quickly your battery just goes away. I don't know. I found Zoom is just terribly optimized, or it's just, you know, the nature of a application that streams like 1 million videos. All right. Welcome, Samir. You can't hear me yet. Stephen, don't worry about that. I am prepared as an event host, or at least I did my best to prepare. But you know, if everyone wants their chicken code, there's the chicken code, and now you can use it to, you know, be able to buy store merch because now it's finally here. So there's that. All right. I guess we'll get started. It's more or less 5:05 p.m. So I've given everyone ample time. So anyway, welcome everyone to my workshop on how to deploy Facebook.com. Now with more uptime than Facebook. That is a reference to the terrible issue that happened a while back with regards to Facebook, where their entire website went down for like a couple of days. That was a funny one. Anyway, before we can get started, the checking code was on the slide. I did not notice. The checking code is Facebook with capital Face. You can also use this QR code on your phone to quickly check in without even needing to use like a link or logging into the platform. You just have to be logged on to the membership portal and you can use this QR code to easily check in and not have to deal with opening up 1 million tabs. I will leave this for a couple minutes or like a few seconds actually. And I guess you can check in later and we'll get started. So first off, I'd like to start off the workshop with a little statement, which is psych. I'm not going to actually tell you how to deploy Facebook.com. So this workshop has a little bit of a clickbait title. Unfortunately, I am not a Facebook, or rather Meta, employee, so I don't know exactly the specifics on how Facebook.com works. I only know that it is a PHP application written in Laravel, so that is the most of what I could tell you with regards to how to deploy it. But this workshop isn't specifically about Facebook necessarily. It's more generic. So I'll give the couple of disclaimers I have. We'll be talking about a lot of stuff. We'll be talking about all kinds of infrastructure. We'll be talking about basically all of the basics and also all the way up to pretty much what Facebook and Google and FANG does today with regards to infrastructure. I'll be explaining what infrastructure is. And generally, we'll be going very conceptually. Another thing that I would like to kindly tell you is that I talk a lot. I think most of my friends would confirm that I talk nonstop, and I just have this tendency to not know when to stop. But you are here, and thankfully, there's this wonderful feature in Zoom called Raise Hand. So I will kindly ask you to feel free to interrupt at any point in time when you have questions in lecture by typing in chat or raising your hand. I'll pay attention, and I'll make sure to take a little bit of a break and answer any questions you have. Please ask questions. There's a lot of concepts, and this workshop will be quite dense. And I would like to, help you learn as much as I can. And also, we won't be coding today or writing any code, mostly because writing code for infrastructure or doing any practical stuff in that regard is pretty difficult when you get started, especially because it can become destructive, expensive, and also can be a little bit risky in many different fields. I will be showing you examples of stuff, but there won't be any sort of like interactive part. But don't worry, this workshop will be as interesting as I can make it to be, which is very interesting and fun, and it will be definitely interesting. Kernel level C, I am not going to show you that because that is, if you want to know that, you can take 120 free as a course next quarter if you're so inclined. Also, I'm going to try as best as I can not to get interrupted by chat, but as we well know, I love to talk, so I probably will get interrupted. But regardless, let's get started with the number one question, which is, what is systems engineering? Well, systems engineering is about maintaining technical infrastructure. Now, what does that actually entail? Well, it entails, for all intents and purposes, the metaphor of infrastructure in real life as well. So for example, the infrastructure of the real world is roads, pipes, and the internet, networking in general, that also included. And that is what systems engineering handles as well in the field of computer science. The concept of handling the technical infrastructure needed to run applications, which is servers, low-level stuff generally, networking, routers, and lots of complicated stuff. There is a lot of intersection between systems engineering and SWE, mostly because in software engineering, you write a lot of specific and intricate systems and components, whereas while in SWE, this is a lot more high level. In systems engineering, this is a little bit more low level kind of stuff. You deploy the front and back end of the databases of actual web applications rather than much else. And also a similar component that is shared between the two of them is that you have to understand the components of all of the parts of your application to understand that. And that is also something you do in software engineering as well. You might have not necessarily heard of this as systems engineering. You've probably heard of this area as a DevOps or SRE or sysadmin, but they mostly cover the same concept of taking low-level parts of infrastructure like servers and managing them properly. Now, why is software engineering, systems engineering? Why would you do this? Well, first off, software needs infrastructure because, believe it or not, no website can exist without hardware to run on. And because of that, this is a very critical part of software. Just as you need to know how to make a front end, a back end, you also need people to deploy the front end and the back end somewhere in order for the web application to be accessible for other people. Systems engineering is also needed because of on-call duties. Believe it or not, in CS, stuff breaks. There can be bugs, there can be issues, and generally, the software engineers are not necessarily always there. Sometimes they may be, on vacation, or the person who wrote the code might just, have finished their day, especially in companies that span the world because time zones are a thing. And because of that, stuff breaking is important. You need to fix the things that end up breaking. And typically, systems engineers are the most qualified to immediately triage and fix these problems because they are the ones that can very quickly identify what parts of the system are not working, including front end, the back end, or even any other low-level part of the infrastructure, and very quickly ping the teams or even perhaps fix them themselves in case something breaks. In other words, systems engineering is needed because they are the most qualified people to put out fires. And also, Linux is a very good reason as to why systems engineering exists. Believe it or not, Linux runs the world right now, whether it be your own computer or anyone else's computer, even the servers that run the computers all around the world, and that run, the internet. And as such, it is a requirement to know. And sometimes it is too much to look at the high level stuff and low level stuff at the same time. So you need sort of a disparity for it. 1 second, it is very cold. I'm going to pause the recording if I can pause. Sorry about the interruption. I had to put on a hoodie. I ended up being fashionable. Sorry, Sean. Anyway, now, what is generally entailed when it comes to systems engineering? What parts are actually covered? Well, first off, more or less systems engineering can be fun. Why would it be fun? Well, first off, you get to automate everything. You get to pretty much take every single part of your application and automate it. You also get to understand everything because a systems engineer has to look over pretty much everything that occurs in an application in order to get it to run. And you also need to sort of be able to do the triaging and fixing that I mentioned earlier. Now, it is also risky. Every single FANG outage that I have been able to see in the past 3 to 4 years has been entirely due to human error in systems engineering. And this is just the reality of it. It is a difficult field because there are a lot of moving parts, as you will see later in the workshop. And if any one of these gets faulty or breaks or is not managed properly, it is a house of cards, much like front ends and back ends and every other part of the application. It's just a different part of computer science that needs fixing. But risk is excitement. I mean, at the end of the day, if something isn't risky, it's not a story worth telling. Like when we are going to talk about, our college life years from now, we're going to talk about the days where we were doing our homework right before the deadline. We're not going to talk about that one time where I finished my homework a week early. Risk is excitement. And in that way, systems engineering can also be exciting because whenever you do things, they can end up being entertaining. Nothing beats the feeling of working on a production database in order to migrate data and fearing for your life that you might accidentally delete all of the data of an application, which, by the way, happened a week ago for us. The portal backend got updated to let store happen, and that was a very entertaining process, especially for me. Now, why should you do syseng? I mean, everyone wants to become a SWE, and you can also choose to do syseng. And one of the reasons why you might want to do syseng is actually money. Turns out that on average, not in every company, but on average, SREs are actually with a higher starting and salary pay than SWEs or equal. At most FANG companies, the salaries are equal because SREs are considered SWEs. But in smaller companies, or especially companies in the international field, SREs are in high demand because they are rare to be found. And you might find that you might actually get paid more for doing these things. And even if SREs do not get paid more than SWEs in terms of salary, on-call duties are compensated over time with bonus pays, essentially, as if you were working overtime and you get compensated a lot for it. So either way, even if your salary is not as high, you might get compensated for being on call for however many hours your shifts are. So you might find that a very motivating factor to join syseng. But you might also like it because it's informative. I mean, you get to learn the full stack of any application by interacting with the individual components that make it. And that allows you to, learn more in the field, and perhaps you might enjoy that. And it's also fun because, like I mentioned before, risk is excitement. Sorry, I jumped with my slides a little bit there. So we'll get started with the actual part of the workshop. I'll start describing as an overview the basics of infrastructure management, and then we'll get more into the specifics of complexities as problems arise. But we'll do this under the story of you wanting to deploy your own web application, right? We'll sort of follow the story of your own web app, and we'll see what ends up happening. So part one. So you want to deploy an MVP, right? You did some work, you did some coding on a web app. It could be whatever you want. We'll call it, I don't know, awesomewebsite.com. And now you're done and you want to show it to the world. Well, first off, like any systems engineer, you need to find out what are the individual components of a web app. And at this point, hopefully, I assume if you all have attended ACM Hacks workshops or most workshops, you probably know the three main components of a web app. The front end would be the first one. And it is very important to analyze exactly what each component entails specifically, right? Not just what they are in terms of names, but also what they are in terms of specifics in what each one entails. So for example, for the front end, it's more or less an HTML, CSS, and JavaScript application. I mean, it's not much more than that. It is just a bunch of static files. Now, your browser interprets the JS files and makes a dynamic application, but from our side, that's irrelevant. From the side of a systems engineer, all we care about is that it is just a bunch of files that your browser needs to download. Now, there's also the backend, which is a REST, CRUD, or GraphQL API, however buzzwordy you want it to be. And it is likely a node process or some other language. I mean, it's just a program that you run, right, at its basic, at least from our perspective. It's not, we're not going to look at the specifics of how web apps run. We're looking at the components that are running because we were working at the lower level. We want to give them the ground to work on, not how they work on specifically as of right now. And there's also another very important component, which is the database, right? The database is sort of dismissed and thrown away to Heroku or some other platform to manage, but that is also something that we need to take care of, at least as a systems engineer, especially if we are hosting it on our own servers. Now, the front end, like I said before, is a bunch of static files. So we can just serve these files, and we've solved the part of managing the front end. How do we serve these files? Well, we can just set up an HTTP file server. There are many of them, one of which I will describe later, but essentially we just want to have a place where you can put a bunch of files, like a directory, and you can connect the HTTP server to them, and then the browser downloads them whenever it accesses them. Now, the backend, well, that's a process, right? So it's just an application that you run on your computer, kind of like npm start or whatever your language entails. And it binds to a port on your computer, typically 8080, but it could be any other port. And essentially, when it comes to the backend, we just run it. I mean, it's kind of a simplified process, but at the end of the day, at least from the perspective of running it and deploying it, we just need to upload the files, install our dependencies, and run it, whether it be Docker or systemd or pm2.js. These are buzzwords, if you will, but essentially these are types of runners. Docker you might have heard of. Systemd is a process manager wherein you can just tell it to run a particular program at particular times with particular like limitations and configurations. And pm2.js is essentially systemd but written in JavaScript. It's an option, and you just need to run the process. It's not particularly a weird part to explain, kind of like how you run it locally when you're developing. You also need to redirect it to the internet somehow. I mean, if you run it on your own computer at localhost, we all know that localhost is not accessible to the rest of the world, so we'll need to redirect the backend to the internet somehow. The database, thankfully, is also a process. We don't need to sort of think in a different way. It also binds to a port, and to our extent, implementation is not relevant with regards to the database. What just matters is, again, kind of like how we looked at our web application before, all we care about is running it. So in that perspective, at least, we're kind of fine in that regard. Now, we've talked about the individual components in every single part of our system, but we also want to talk about the things that we need infrastructure-wise to actually deploy this MVP on the internet, not just on our local machine. So what do we need? Well, we'll need a server, which you can get from a million places. There are lots of cloud providers in the world. There's AWS, there's Google Cloud Services. You've definitely heard of these, but there are much simpler ones that I recommend using that are definitely cheaper and also easier to grok and understand. DigitalOcean and Linode are what are more referred to as VPS providers, virtual private servers. And they essentially give you, for $5 a month, just a very simple Linux server that you can run and you can use to host your application. You will also need a public IP address, not a private one. Localhost would be considered a private address. Thankfully, though, DigitalOcean and Linode and most services provide a public IP address with their VPSs. Otherwise, I mean, how are we going to connect to them outside of their own consoles? So thankfully, that is not that difficult to acquire. If you were to buy a physical server rather than one from a virtual private space, you would have to buy an actual IP. Thankfully, though, that might not be an issue, especially if you're deploying an MVP. That might be an issue later on down the line. And believe me when I tell you, you don't want to think about that right now, because public IP addresses can be very, very expensive. But thankfully for DigitalOcean and Linode, they're just a $5 a month cost, and it's not the end of the world. You'll also need a domain. Like every good website, you want to have an awesome domain to point it to, such as awesomewebsite.com. You can buy one from Google Domains or Namecheap, and also DigitalOcean and Linode provide their own domains as well. When you buy one, you just have to pick a good name and you can use it as well. And just like I said before, you can generally get all of these from the same place, because you essentially can get it from a cloud provider, which is the equivalent of infrastructure as a service. Whether it be AWS or GCS or any of the ones mentioned above. So what do we need to do step by step to deploy the MVP? Well, first off, we need to set up the DNS for our cloud provider. Now, what's DNS? Well, DNS is the domain name system, and it is the phone book of the internet. When you type facebook.com in your browser, you are actually telling the browser to contact the domain name system to find the IP address of facebook.com, which is whatever IP it is. I have no idea right now, but essentially you are telling your computer to look for the phone booth and find the actual server. And similarly for our website, rather than remembering a set of numbers, you're going to want to, somebody is talking. I will need to mute them. Oh, we're good, I think. There we go. I don't know how to set the automatic muting on join, so we'll just live with me manually muting people. Now, to set up the DNS on your cloud provider, thankfully for a simple web application, it's actually quite easy. You need to set an A record. A record being a very simple concept in DNS, which is simply, if you look for this domain's A record, I will give you the server's IP address for this application. That's it, for this domain. I will just give you a number of an IP address and you can connect there. So for our application, we would just set the A record for both our front end and our back end to the server's IP address. I see a couple questions in the chat. I thought domain was stuff like .edu, .org. That is correct. Those are actually top-level domains. Top-level domains are not controlled by the cloud providers. They're actually controlled by ICANN, which is the International Committee for Authoritative Name something. But essentially, ICANN handles the top-level domains and also hands them over to other countries in case they want to own them. You cannot typically own a top-level domain unless you are a big company, but you can typically share it with other people, which is what you do when you buy a domain like, say, acmucsd.com or awesomewebsite.com. Those are domains that you own, but they are subdomains of the top-level domains. And for example, google.com, again, is a subdomain of .com, and so on and so forth. I also noticed Tristan saying when Facebook broke their DNS, that is technically not true. They did break their DNS, but it was actually a lower level of the DNS. I can respond to that question at the end of the workshop. But anyway, now that we've set the domains for our website, we want to put the front-end files on our server. We can put them in any directory we want. It's just transferring a bunch of static files anyway. So thankfully, that's not too difficult. To do that, you would probably use something like SCP or SFTP, essentially a file transfer protocol, and just transfer them onto the server. There are plenty of programs that can do this. You could even do it in the interface for some of these, like DigitalOcean. But you can do it with, say, CyberDuck, which is a free macOS app, or you can do it with Termius or Putty or FileZilla. There are plenty of applications that are used for file transferring. And after you put the front-end files on the server, you want to start the database and API servers on the server. You want to start the processes and just tell them to run. And that's it, right? We're done with deploying. All we have to do is just go to our browser and access acmucsd.com or api.acmucsd.com or awesomewebsite.com, whichever one you want, and you will find the website that you deployed. Now it's all come together, right? We have all of our steps. We have the front end, we have the back end, we have the database, all of them connecting together, kind of like they do on a local server, but now they're doing it on a remote server. So you can access it from anywhere on the internet. The thing is, specifically here, we need to talk about port 80, which is we want to look at, which is the standard HTTP port that everyone has agreed on. Generally, it's agreed that if you want to find an HTTP server, you look at port 80. That's just how it is. There's similar standard ports for all protocols. SSH is 22, SMTP, which is mailing, is 25, and they're just numbers that people address to when they go to the IP address to find the part where they want to communicate with. So it allows one server to have multiple things it can do rather than just the one part. So port 80 is the standardized HTTP port. There's also 443, which is the HTTPS port, the thing that gives you the green lock on your browser. And that's a different part of the process as well. But the thing is, if we want to use one server for both the front end and the back end, we will end up with a bit of a problem. We can bind the front end web server that serves the files to port 80. But we can't do that for the backend. Why? Because Linux hates you. Linux will not let you bind two processes to the same port for a fairly logical reason, which is how would Linux know which one would you actually want to access, right? How would Linux know if you want to access the port for the web server or the port for the API if they were not completely different servers? But that's a problem because we want to have both of them accessible to the internet. Thankfully, though, there is a quote that I heard in CSE 120 that I love a lot, which is that every problem in computer science can be solved by another level of indirection, which is true. Even this can be solved by a level of indirection. So remember that the problem we had was that we can't bind two processes to the same port. We can't bind both the front end and the back end at the same time. So what if we bound one process? What if we bound one single process to port 80 that indirectly linked to the front end and the back end, and then we can sort of use that magical process to know whether you wanted to access the front end or the back end. And that is done using an actual program that exists, which is called a reverse proxy. The reverse proxies are essentially, I say quote unquote, because they're not really just that. They're key value stores for domains in the sense that when you access a server with a reverse proxy and you access it with a particular domain, it will know that you accessed it with that domain, and it will know, okay, look, if I am told to access this domain, then I will point you to this particular program that is under that domain's name. So for example, if you will notice on sort of the internet cloud would be considered a reverse proxy in this situation. So say, for example, user's device A contacted our server with awesomewebsite.com. In that case, the server would know that you accessed it with that because you are putting that in the header of your HTTP request. And then you can just go there and it will go, okay, you wanted acmucsd.com. Perfect. I will point you to this part, which is the front end. But if you wanted api.acmucsd.com, then that means, all right, well, you wanted the API. So in that case, I will point you to the other process, the backend, right? So it just looks at your domain and redirects the requests from the same port, from the same IP, as if they were different. Now, throughout the workshop, I have these expert mode sort of boxes. I will talk about them briefly, and they're like more advanced knowledge. You don't need to know about these. Technically, reverse proxies redirect by any filter and to any interface. They don't necessarily have to be specifically to the same computer as different ports. They can also redirect to different servers entirely. Reverse proxies can also redirect by different filters. They can redirect, for example, if you go to a particular subdomain or if you go to a particular subpath. So for example, if I said acmucsd.com/store, maybe I wanted store to redirect to a completely different server. That is also totally possible with reverse proxies. It's just, the concept is that it's just a key value store of, if you access it with these filters, I will point you to one particular server. And that solves our problem of binding to port 80. And that's it. We've deployed our application. Reverse proxies do come with a few other cool things that are not required, but are pretty nice. They come with TLS certificate management, which means that they handle the green padlock automatically on your website, so you don't have to deal with the problem of doing a whole bunch of other checks for it. They also come with logging, so you know who accessed your website at what time and in what location. And they also come with caching if you want. So if you have a page that you know will stay mostly the same, the web server won't have to constantly look in your file system to find the page and load it and then send it. It will just keep it in memory and send it constantly, which saves time and your disks, because physical things can wear out over time. And it can also handle compression. Most websites give some form of compression to files, notably gzip. So if you access, say, facebook.com, a lot of the original files are just gzip compressed so that they take less space on the network and they download faster. So it's just better for your computer network connection. Don't worry about implementing these. They just come with reverse proxies. Notably, Caddy is a powerful reverse proxy, if not one of the best nowadays, which you can use to do all of the stuff we pointed out before. Nginx and Apache are common alternatives. Nginx, actually, not Nginx. I'm the one that makes that mistake. Nginx doesn't handle the certificate management part. It doesn't automatically do the green padlock, but it is much more powerfully like filtering than Caddy. And Apache is just the default installed on almost every computer. It's useful, but sadly Nginx and Caddy have kind of eaten its ground. This is an example of a reverse proxy's Caddy file. Sorry, the Caddy programs configuration file called the Caddy file. And this is, for example, something that would sort of represent how we would deploy the portal, the membership portal for ACM if we were to use Caddy. We don't, but that's a different story. For example, this is the name of the domain right here. Let me get a pointer. Do I have a pointer for, I don't actually. I will just annotate on Zoom. So this would be the domain of the website. As you can see, it's just the domain of the part that we want to filter. So if I were to access our server with this domain, then I am telling it to reverse proxy your request to port 8080, where the backend is actually stored. And for example, if I were to access members.ucsd.com, where our actual portal front end is, I would just tell you to look in this folder where all of the static files are hosted and just give a file server. It's a very simple file, pretty self-explanatory, and it does the job completely automatically, and you don't have to worry about it. And with all that, congratulations. You have deployed your MVP, and we can now sort of abstract these specifics away into one single block of a server that gives to the internet ports 80 and 44 free, and you are just done. You have deployed your MVP, and congratulations. Now, what's next? Well, this is perfectly fine. There is no need to overcomplicate the system if this works just fine for your MVP. If your website is just a small website that serves a limited amount of customers, you don't need to do anything more than this. This is perfectly fine. One server is enough, and you don't have to deal with complexities or little things that might annoy or somewhat detract from your time spent that could be better spent coding your actual platform and bringing benefits to customers. Sysengines can do that. I mean, there are technically suites, and at the end of the day, this is perfectly fine, especially if you're just getting started. Now, let's say some time has passed. Let's say that you have sort of, had your website for a couple months. It has been around the world. People have shared it and it's been being used. And it turns out that you end up on the front page of Hacker News. Congratulations, you can go call your mom that you got on Hacker News's front page, and that's perfect. You are now more popular, right? You've gotten a sudden burst of popularity. However, while the MVP person, website coder of you is happy that you ended up on Hacker News front page, your systems engineer side of you will not be, because if you Google Hacker News front page, you will not see the fact that you are popular. You will only see the DDoS attack, because most times when Hacker News puts, ends up having a particular website being popular, you will end up with the hug of death. Your website will stop working because there will be a sudden inburst of people that come to your computer and try to get your website, and it will just not be able to handle the load. So we need to scale. We need to take that initial server, that beautiful small server that we deployed, and we need to make it bigger. Now, remember, I said to keep it simple. So for now, we're going to try to keep things simple, in which case, if you have a localized sort of situation, if you just have a small little peak in time, you can just increase the amount of hardware that your server has. You can add a RAM, CPU, disk, network bandwidth, whatever it is that your website is currently having trouble with, you just add more of that, right? DigitalOcean and Linode and all of these websites have plenty of ways to tell them that you want to have more RAM or more CPU or more disk storage or more network bandwidth with. You just go into the interface, you click on the various buttons and toggles that they have, or increase your server's general size. You will have to pay more, but it is a justified cost, right? Because you have more customers, and more customers hopefully means more value attained if you are, say like a website that has a subscription or something. And you could just keep doing this, right? But how long can you keep doing this? Because at the end of the day, the more you do it, the more expensive it gets. And more importantly, you can't increase the size of a server forever. You can have a server that is fairly massive. You can have like tens of terabytes of RAM. You can have tens of terabytes of storage. You can have massive CPUs that handle requests. But sadly, physics doesn't like you, because at the end of the day, if your website grows insanely because of Hacker News, if you end up being as big as one of the Fortune 500 companies, you would need to have an infinity computer to handle all of this traffic, right? You would need to handle infinite terabytes of RAM, infinite terabytes of storage to handle all of these requests, all of the new data that you're attaining. You would need infinite CPU frequency to be able to handle all these requests. And let's not even talk about network bandwidth. And sadly, that's not possible. The laws of physics state that you can't have anything that is infinite. And even if we dismiss the concept of an infinity computer being impossible, even if we assume that is possible, physics still doesn't like you, because there's another law of physics that you have to circumvent, which is a very simple one. Nothing is faster than the speed of light. And that includes your network connection. If you have your infinity computer in LA and you have a person that is accessing your website in San Francisco, that's fine, right? It will be fairly quick connection. But if you were to have a person that was in Europe, in Germany, or in Britain, even if you were to drag a wire, an optical fiber cable through the ground, drilling through the earth all the way to that other person's computer, you would have at minimum 54 milliseconds of travel time. So that means that at minimum, it would take 54 milliseconds for anything to happen. And while that sounds small right now, remember that we are ignoring a lot of things, primarily the fact you have to drill through the entire earth to do it, which you cannot do. You also need to put optic fibers everywhere, which is not possible because not every part of the world has optic fibers. You would need a direct link, which is there is no such thing in the real world. You would also need extremely fast routers because there is no direct link, and routers are slow and they have performance hits. And even if you were to have all of this stuff perfectly, you can also chalk it up to human error. I mean, you can have somebody who messes up and has a router that isn't working. You can have Facebook go down and all of a sudden none of the internet works anymore, right? Like there are plenty of problems with having one infinity computer in one place and handling traffic from all over the world. You just can't have that happening. So we need to get closer to the user, right? If we have a server in Britain or in Europe, we would need to have customers there as well. And if we have servers everywhere around the world, then we will be able to have less latency for every single person and be able to serve them better and faster. And this is what is known as edge computing. It is the concept of bringing servers closer to users, which is a requirement for websites that become huge. It saves on latency and bandwidth, which also provides a better user experience, and is basically what video game servers do, right? Like when you have a game like League of Legends, right? There are different regions for the game: Europe, North America, Asia, etc. There are different regions where you can access your game, and those different regions have different servers in different parts of the world and decrease your latency. Now, obviously, for a web application, that is not necessarily as important, but it can be important for web applications that are time sensitive. For example, if you're, say, a financial tech application, you need to be fast, because if you are not fast, then somebody who is faster than you will be able to take your place, right? They will get there first, which is not a good thing. Unfortunately, edge computing complicates deployment by a lot. And what I mean by a lot, I mean that we will have to deal with a ton of problems. But let's get started. Let's assume that we convert that one server to 100 servers, right? However many servers we need to handle all the traffic all around the world. But there is a problem with that. Not only the problem is that there are different IPs, right? We cannot use all of those IPs in the same place. Every different server needs to have a different IP address. And remember that our domain pointed to only one of them. So we would need to have that one domain point to every single one of these servers in order to be able to serve them. Now, that's not very easy to do. And also you can't do directly because DNS doesn't provide that functionality, at least not simply. So we need another level of indirection. Now, if you remember, we had the reverse proxy that bound to the port. But what if we had a different piece of software that did the same thing, but for domains? And that exists, and it's called a load balancer. Now, load balancers essentially do a very simple job, which is that they split the load evenly across machines. They take one request, they send it to one machine, and then another, and then another, and then another. Most reverse proxies can do this, and they do it automatically. And you can have one IP and one domain, but serve on multiple app servers. Now, you can also have an issue with this, which is notably that the one load balancer would need to be somewhere in the world where everyone can access equally, but that decreases your latency. Fortunately, there is a solution for that, notably that you don't need reverse proxies for load balancing. You need multiple DNS records that allow you to route robin between assigned servers. And you can use that to point to all of the servers all around the world. But unfortunately, that's not necessarily very controllable by you. The client can have full freedom of what server they actually access. And you may want to use a different load balancing policy depending on what your servers do. And the DNS service, the domain name system cannot know that, right? So you will need a different system. You would still need load balancers in the end if you want to have your application be fully performant, but you don't necessarily need it immediately. Additionally, DNS can be restricted to regions of the world, depending on like latency. So you can have different DNS records point to different servers, but preferably you would have your own load balancers. And you can have one or two or many, depending on how many servers you have, putting them also all around the world and splitting your load evenly. But the problem with that is we end up with another issue generically, which is that if you remember our original setup for a server, we had the front end and the back end of the database all in the same place. But the problem with that is that the state differs from server to server, right? Because the database is stored individually on every single server. And because of that, if I were to say access awesomewebsite.com in Europe, I might end up with a different state than when I was in the US. And that is a problem because it would be kind of weird if I were to make an account in the United States and then suddenly travel to Europe and all of a sudden have my account not exist. So we need a unified sort of server, right? We need a unified system for all of our databases. Again, every problem in computer science can be solved by another level of indirection. So just add a database server that is completely separate from the original servers, and then have that server be the one that every single other app server accesses, and then have that be your system of accessing the same amount of data everywhere. The problem is the previous code that I told you has a little bit of a caveat that I didn't mention before, which is that every problem in computer science can be solved by another level of indirection until you encounter another problem. The problem here is that we have one database server, and with one database server, we end up with the physics problem that we had before, right? The speed of light restricting us, or even hardware restricting us. So we don't need just one database server. We need more of them. We need as many database servers as we can in order to serve every single part of our system. We need as many app servers as we can to deal with every single part of our system. But with databases, we end up with yet another issue, which is that the state differs from one database server to another, right? You may have one database have a certain amount of data and another database have certain other kinds of data. And that is also a problem because you need to have the same data all across all your database servers. Now, the problem with that is we need replication. And replication, thankfully, is implemented by most servers. The idea is that all the database servers cooperate with each other and they replicate their data across all servers, right? And this is done with sharding in MongoDB, which is the most known method, which is that every single small server sort of keeps their own chunk of data. And then if required, another database server can hit it, which localizes pretty easily and scales quite well. There's also master-slave replication in SQL databases. You will have to excuse the terms, but SQL databases have existed for far longer than our current climate has. So, the names might not be very well done. Master-slave replication is for most SQL servers, and as a concept, master servers can be read and written to, which means that you can write database requests, and slaves can only be read from. So you can't add new records to the database. This is useful because you can have slave servers all around the world, and it is far more likely that you will be reading more from the database than you will be writing. So this reduces latency for most phenomena, but not for all of them, right? You can have multiple masters though, and multiple slaves. That is also a thing that you can have. Other common methods of replication include just A/B replication. The idea is that you have two different database infrastructures that are identical all across the world for full redundancy. And if one of them goes down, you can just use the other. The problem is this can be very expensive, it can be wasteful, and is only recommended if doing orchestration for databases is difficult. So if it is hard for you to handle making multiple database servers, it's recommended to have this A/B replication system so that in case something goes down, you can at least still serve people, and then you can fix the problem later. Hopefully, this is enough. Tawhid says, how expensive? Well, if you were to do full A/B replication, it would be as expensive as your current database infrastructure is, right? So it would be paying for, say, 20 servers for 20 database servers, and you have to pay for another 20 more to have the identical kind of infrastructure. And while that is fully redundant, which means that if all 20 of your original servers go down, you still have 20 others that can immediately pop back in. The problem with that is that it is, well, twice as expensive. And the amount of expense would be somewhere along the lines of, well, a small server would be about $5 to $10 a month. 20 of them would be 200. It would be $400 a month, which doesn't sound like a lot of money, at least for, big tech companies, but for a small business, it can be a lot of money, right? Like paying double for your infrastructure costs is a lot of money that you may not necessarily afford. And bear in mind that when I mean $10 a month, I'm talking about very small and not very performant database servers. I'm talking ones that have small CPUs. So that's not a lot, right? That can be you would need to pay more generally. It could be along the lines of $2,000 to $4,000. It can be pretty high if you use A/B replication. Anyway, I hope we've solved most of the problems so far, right? This looks good to me. We have different load balancers all around the world that can handle multiple servers all around the world, app servers specifically, and we have replicated DB servers all around the world that can handle requests in certain locations better and in particular parts. And hopefully that's enough, right? And it works. That is fine. The problem with that is, what about updates, right? If you were to change a part of your application, you would need to update the application. If you have a security vulnerability in your database, you would need to update that as well. If you have your load balancers needing an update as well, that can also be an issue. Updates are something that happens a lot. And the problem with that is that if you change anything about the setup, you need to update it, right? And let's assume for sake of simplicity that the update process is known to you, right? Which is a pretty fair assumption. I mean, everyone knows how to find a Google article telling you how to update a Postgres database, right? We'll assume that you know the process and it's very clearly laid out for you, including for your own application. Are you sure you want to do that though? Because if we were to look at our original setup, this is us needing to update the load balancers, the servers, and the databases in almost every situation. And think about the servers, right? You need to update the front-end files, you need to update the databases, you need to update the backend. When you update the databases, you need to migrate them, which means that you need to take the current records in the database, the current tables, and modify them in a standardized manner so that you can update to the new functionality your database needs. And you need to do this manually for every single server. You would have to go to every server in the world and write, your scripts, write your installation process files. And that is a lot of servers. I would have to sit there and go through who knows how many servers, depending on our application, and do it manually. But thankfully, we can automate things, right? We're CS majors after all, right? We have to automate everything. And recall that the update process is known to you. So you could just write a shell script. Well, just write a shell script. I mean, shell scripts, as we know in 15L, are not necessarily very fun to write. I think we all can agree that the scripting projects for 15L were not very fun because shell scripts are hard to write. They're error prone. They can fail immediately. They have an arcane syntax. They're also not idempotent, and they're also not code we're used to normally write. If you're wondering what the idempotent term means means that if I were to run this shell script, the output ends up being the same. So if I were to run a shell script that installs a computer, it wouldn't just reinstall the computer, right? It would just run once and it would know that I installed the computer, right? So that's what idempotent means, the same output for every single run of the script. And shell scripts are not by default idempotent. You have to make them be, which means that you have to be careful to test every single part of your code. You need to write stuff like, is this database installed? Is this database the right version? If it is, don't do anything, right? That's a lot of work for a shell script. Shell scripts are hard to write. And as such, it's not really fun. But trust me, if there's one thing you want to learn from this workshop, which is to automate everything you can, right? And hopefully you would only have to automate the process of installing things once, right? You would have to automate the process of updating your servers once, and that would be done. But that's not everything. That's just automating the upgrade process. But can we maybe automate shell scripts? Could we possibly automate the process of generating a shell script that then updates your servers? Yes, we can. We can programmatically make small segments of shell scripts that are run for every individual part of our update process, and then compose them together for a server, and then run it and make it idempotent, and then run it on every single server, right? Which is a possibility for our process. But automating that can sound pretty hard, right? I mean, we would have to do all the things we did before and add another level of indirection. Thankfully, though, you don't have to do that because somebody already solved this problem, and it has been solved by Ansible. Ansible is a tool used by systems engineers to create what is referred to theoretically as configuration management. One second. Now, configuration management is essentially the concept of taking a bunch of servers and making them look exactly the same. And Ansible has terms for the different components that this needs to make happen. It has playbooks, which are the description of what your infrastructure has. They're the description of the app servers, of the database, and the load balancers. They just say, look, each individual one of these needs to have these particular things installed in this particular way. There are also roles, which are essentially types of descriptions, right? They are in the sense of telling the server that, telling Ansible that, look, app servers are of the role app, and they need these things installed and these files transferred and these things done. Database servers in a similar way, load balancers in a similar way. And groups in Ansible are essentially IPs of servers that have particular roles. So you can have a group of servers that are your load balancers. You can write the IP for every single one of them or the domain for every single one of them. And then you can point to them as saying something along the lines of, look, this group will have these roles and these roles need to be installed. And as an example, this is a segment of the role for the breadbot server. Breadbot is our ACM Discord's bot. And this is the first free tasks in the Ansible playbook role for breadbot. So as an example, I can explain each part of these lines. It's a YAML file, in case you're wondering what kind of configuration language it is. So this would be a task, and the task says something along the lines of ensuring the user for breadbot exists. I personally enjoy having applications run under different users. That's a personal preference. You don't have to do that. But this role essentially tells Ansible, look, this server needs to have the bot username existent, and you can add the comment of it being the breadbot account. And Ansible will ensure when it runs, it gets to the server, it looks for the bot user, it looks for the comment. And if they're not the same, both of them, it will make them, right? If the bot user doesn't exist, it will create it. If it does exist, but it has a different comment name under it, then you can assign this new comment. And if it does exist in exactly this form, we don't need to do anything else. The script also installs dependencies. So it will run the apt module is what this is called. It will look for these packages, which are G++, the GC compiler and make, and it will make sure that they are of the latest version. So it will look over the computer. It will look over the packages that are installed. If they are of the latest version, perfect. We don't have to do anything. If they're not, it will update them for you, right? And you can do this for your database as well. You can say, look, I want Postgres to be of the maximum version or the latest version, my bad. And also this last one is a more clear one. To get the latest version of breadbot from GitHub, and you can do it as well. If you want to see breadbot, it's available at this link. And it will tell Ansible to clone the Git repo directly in this destination at this particular folder. It will create all the folders beforehand. It will clone the repository there, and then it will make sure that it is of the latest version. Obviously, this isn't it for Brevbot. There are a few other statements like these, but for the sake of brevity, I didn't put them in the slide. But this is generally how an Ansible role playbook looks like, right? It's a very descriptive thing, a very easy to read thing, and you can use it later. So these are the advantages, right? It's declarative, which means you write it once, and it's idempotent, which means that it will make sure that those things happen. That's it. It won't do any changes if they are already there. You can run it with one command, and all of the servers will be up to date and ready to go. And it's easy to read once you learn it, right? So you don't have to write insane shell scripts to get it to happen. And you can have Ansible manage the load balancers, the servers, the DB servers, and it will just take them all at once. It will sort of update each individual part individually, and you won't have to think about the process of doing it manually anymore, and all will be well with the world. Sorry about that. A plane passed by my apartment, and it was very loud. Anyway, all is well with the world, right? We have all of our servers managed, and like I said, they're all managed by Ansible. And well, that's pretty much enough for scaling on an international level. I mean, this is probably what 90% of companies do. I wouldn't know exactly, but they mostly do some variation of this if they're working on a massive scale, right? They have multiple load balancers, multiple servers, multiple databases, and they're all managed together with some kind of configuration management tool. It doesn't have to be Ansible specifically. It can be, there are other versions. There are also versions like Puppet, and they all have different implementation variations, but the concept is the same. You have the different servers, you have configuration management set up, and you run it to update your application automatically, and you don't have to deal with the specifics of scaling in the sense of other things. You would still have to deal with making new servers and deleting servers if you want to increase or reduce your costs, but not much else in that perspective. This method is effective, versatile, and it's theoretically infinitely scalable. You can do this for as much as you want, really. But it is important to monitor what you scale, because if you scale for no reason, you will end up paying more money than you should. So you need to be careful when you do that. This is an example of a monitoring dashboard. Particularly, this is called Grafana. And this is just an example picture I drew from the internet. But you can keep a page like this as a systems engineer and look over, the logins and the memory CPU usage of all of your servers, and just make sure that if anything spikes, you increase the number of servers you have and the configuration management tools. And if it decreases, you can destroy servers and to reduce your costs. And that seems to be it, right? That seems to be all we have to do to manage a worldwide website and deal with all of the problems that one comes with. But scaling is manual, right? We still have to go for each server. We have to instantiate the server on the cloud provider. Then we need to write the Ansible playbook for it. We need to put it in the groups. We need to run it. And remember that I said we want to automate everything, and we're CS majors. And let's talk about the problem that this is kind of boring, right? And easy and simple is boring, right? And we don't want simple. We want fun, exciting. We want buzzwords all over every single thing that we make, right? So that we can pad our resumes or just enjoy when we go to the bar. So as a part free, we will go with buzzword overkill. We will take every possible thing that we can install to make our infrastructure completely infinitely scalable, and just go take our entire thing and just run it off a cliff and make it run as completely automated as humanly possible. And we start with Docker, right? Because that's a buzzword we all know about. We totally need to throw this in there for any reason. In all seriousness, you probably do want to use Docker nowadays. If you don't know what Docker is, it is an implementation of a concept called containers. Containers are static deployments of your application, which means that you just have all of the dependencies installed already, and they look exactly the same. And you have a guaranteed miniature VM running on that engine that is exactly the same across anything that can run Docker, which is useful in case you want to maintain a immutable application, right? You want to make sure that all of your applications that run in the world look the same. You don't want them to be different, in which case this is very useful. It is less difficult to run than actual virtual machines, but it is not as isolated, right? Which is the trade-off here. But it's a good trade-off. I mean, for app servers, you were going to run it on Linux anyway, right? You don't need to make a VM for it. So you can just use Docker to run it and you're done. And this avoids, like I mentioned before, configuration drift. Configuration drift occurs basically when Ansible is not run consistently. And thanks to that, I cannot believe the plane passed by again. This is the San Diego thing, Stephen. You are correct. It is funny when planes pass by. Somewhat funny. But anyway, returning to what I was talking about, Docker avoids configuration drift, where this occurs when Ansible is not run consistently. Because Docker, in all intents and purposes, makes your application completely static in terms of dependencies and configuration. So if you update it all at once in that container, which is useful, especially when you have to deal with very complex applications, which can happen. And the reason why you also want to avoid configuration drift is that the Docker container will not be affected by what happens to the operating system underneath, outside of the possible phenomenon that the Docker daemon stops running, which is a pretty bad one. The more ephemeral your app, the more detached from your actual server is, the easier it is to update and scale. Because, for example, with Docker containers, all you have to do is just update the Docker container and you're done, right? You don't need to like deal with a bunch of dependencies on your machine. You just have to deal with that one specific one, which can be useful if you want to quickly destroy and make changes to your application fast without having to, do a lot of Ansible running on your servers. Thankfully, Ansible can manage Docker containers. So during the process of moving your application, you can use Ansible to take the parts out that would install your application and just install Docker containers instead. An important thing to note is that you don't want to put databases in containers unless you really, really have to, because containers are ephemeral and static, which is not what data is. Data is the opposite of that. Data is not only needs to be volatile to keep track of all the reads and writes that happen, it also needs to not be ephemeral because you don't want to lose data. So it's recommended your databases, even as tempted as you might be, to keep them well away from anything related to Docker, unless you're debugging, in which case that's fine. But you don't want something that is consistently used by people to be in a Docker stack, because it can disappear at any time, and then you might have an issue with finding the data that you lost for your users. This is more abstractions, but Ansible still is not scalable enough if you're dealing with buzzword overkill, right? If we want to be as completely malleable and automated as possible, you still need to do a lot of stuff with Ansible. You need to edit files a lot because you want to change the various parts of your files to make your infrastructure look like them. You need to run files a lot. And you also need to communicate with the cloud provider a lot. You need to create instances nonstop, and you need to do that manually, because Ansible is a configuration language, not a programming language, which means that you cannot write logic easily in it, right? You need to write essentially very declarative stuff, and writing declaratively is possible, but imagine writing something like if this, then that, and run a bunch of functions in a declarative language. You need to write a lot, and it's not worth it. So we need something cool. We need something that everyone has heard about, something that I've been avoiding to talk about this entire workshop. We need something that is automatically scalable, that has a declarative configuration, that has an integration with your DNS and your cloud provider, and you need it to run with Docker, and that would be Kubernetes. And AWS is the cloud provider, Stephen, not the part of the infrastructure we want to talk about right now. We're talking about handling our Docker scaling, and Kubernetes is the big one. We're in the end game now. It's the thing that everyone in big tech uses, the one that you probably also want to use for the buzzword overkill, right? Which is automatic scaling and management of Docker containers. There's a ton of words and terms with regards to this, and I can explain all of them, but the concept is that each individual group of these manages a different part of what our configuration management did previously. Pods are basically the application or the front end or the back end, the containers that you are running. The nodes are the servers themselves that run all of this stuff. Sets are essentially groups of pods that need to be run either on a particular server or in a particular set, and hence the name, and they generally can have logic of how many you need depending on rules of resources for every worker. As in, if you're running out of memory, you might want to make another Docker container somewhere else, or you might even want to have stateful sets, which are basically sets that only happen in a particular state, and keep track of certain variables. You can have manifests are the files that manage Kubernetes. Helm is like a package manager for Kubernetes. There's a lot of words in there, but essentially Kubernetes is a monolith, right? Like as opposed to the previous components we had before that generally had different, very clearly visible components. Kubernetes tries to take all that and form it into one big thing, right? If you like Unix, though, you will not like monoliths. You will like different things that do very specific things. And you will probably like HashiCorp's stack of components, which do what Kubernetes does, but it's more oriented around the fact of running individual programs. And that's the end game, right? the complete out of the realm world of not having any more concepts of the actual world anymore. You have the concept of servers that exist, right? You still have nodes, right? As for example, you have these, which are the servers that we were talking about before, each with their own individual components inside, but you no longer see them as individual servers. You see them as nodes in your Kubernetes cluster that has a control plane managing all of the various individual logics for the individual logic for handling your application, of scaling it up and down, or contacting the cloud provider to get you more servers or less servers, which is an optional thing, as you can see it there. You can have the scheduler, which manages different tasks at different times. It's all very abstract because Kubernetes' purpose is to abstract infrastructure to the maximum possible level. At some point, when you see Kubernetes, you no longer see the individual servers that are running, right? You see Kubernetes itself, because devs can't really tell where servers would be, right? They just think this is the cluster, right? I deploy my app to the cluster, and the cluster manages everything by itself. And that is what DevOps does, right? You sort of blur this line between the servers that we were managing before the sysengines were doing, and now what developers see when they try to deploy their application, right? It's a very specific kind of world, right? It's the buzz term that we've heard about before. And Kubernetes, admittedly, to its credit, scales as quickly as possible, right? It's a very completely automated method in going up and down according to your rules as to how to deploy your application in almost every domain. However, like I mentioned at the very beginning of this part, this is overkill. Do not do this if you are not Fang. Fang is at the scale of needing Kubernetes because they're talking about billions of requests a second, all of which go up and down at any point in time. They work all around the world with a whole bunch of different projects at the same time. And admittedly, someone manually going through Ansible and editing files would be really, really hard. But Kubernetes can manage this fairly automatically with no human intervention and normally works fine. Other companies might find this nice to have, but again, it is complete overkill, and you probably do not want to jump to this. I strongly want to emphasize that if you are going to start doing systems engineering, do not start with Kubernetes. Start with the parts that are very basic. Start with the concept of deploying a server. Understand the concept of a process and the ports. Take the very small things in part one and use them for your MVP. Let's take the parts in part two and very slowly steer into them. Going to Kubernetes immediately not only can be expensive on the cloud provider side, it can also be extremely debilitating to anyone's ability to manage it, because you would need to learn, admittedly, only one platform. You need to learn how Kubernetes works, but Kubernetes is hard. It's the biggest abstraction there is from servers. And if you jump directly to that, you can end up with a very unfun experience of debugging Kubernetes. There are many horror stories of Kubernetes being impossible to debug and people not being able to handle critical infrastructure problems in time to deal with various downtimes. I mean, look at all Fang outages, right? It took them days to fix them. Look at Roblox's 73-hour outage that released a postmortem today that was caused due to container orchestration. Frankly, though, they do need that amount of management, but it's too much. It's too much for small teams, and I recommend you don't steer into that skid immediately. And that's most of the material I wanted to present in terms of specific things you might want to learn, specific parts and important components of infrastructure management and systems engineering. But I want to have a little bit of a bonus section to clearly illustrate the parts of Kubernetes that exist in the monolith and to sort of understand what steps there are and how you can learn Kubernetes. So we will do that with a little bit of a metaphor. We live in a society, and so do web applications. So I say that I show you, as a bonus section, the life cycle of a service, of an application described as the life of a sweet freshman. So step one, you are born. This is actually more referred to as instantiation. The idea is that you start with an empty node that does not have any concept of your application, and you need, fresh out of your cloud provider, and you need to bring it up to speed. You do instantiation typically in order to have it declaratively, and like everything else, with Terraform or Pulumi. Terraform and Pulumi are examples of sort of infrastructure configuration languages, kind of like Ansible, but for the actual hardware itself. There's an example of Pulumi on the right side. It's essentially JavaScript written code of deploying things on AWS or any other thing. So if you really want to have your entire stack written in JavaScript, you can now do that because you can write not only your front end, your back end, and your actual your like code in JavaScript. You can also write the infrastructure in JavaScript, which to me is pretty funny. But if you're into that kind of thing, you can definitely do it. This is an example of a Terraform block. I wanted to show it real quick. This is the actual Terraform block for Breadbot. It describes what the instance on AWS on the cloud provider looks like for Breadbot. As individual components go, this describes what operating system is installed. Essentially, you don't need to worry about that string. Is basically, it says that Ubuntu should be installed in the instance. This tells you what kind of type of instance it is, how big it should be. It shouldn't be that big. And there are a couple of other configuration sort of key values that demonstrate how the server should be deployed, right? Like, for example, what SSH keys it should have, or what ports should be open. It's definitely very abstract things, but at least this way, you don't have to go to AWS and click on a bunch of buttons. You can just run Terraform. It'll automatically instantiate the instances for you, which you still have to do even if you install Kubernetes, sadly. But the thing is, if you're a SWE freshman, if you're freshly born, you need to be educated, right? Like, you can't just go into society and do nothing. So you need to go for step 2, which is going from kindergarten all the way to getting a bachelor's degree in SWE. Well, maybe you don't need a bachelor's degree in computer science to do software engineering, but you probably will need one if you want to get hired at FANG. So this is the step of configuration management, right? Where you go and take the instance and teach it to be what you need it to be for your application. The basics to get up to speed with society, if you will, which would be to install Dockers and Kubernetes, point it to the cluster, or any of the other things that you might be doing, like using Ansible before. There is also Packer that does this from HashiCorp. It effectively makes a virtual machine image that you can use to configure your server. And as a bonus, what if we didn't need to do configuration management at all, right? I mean, we don't have to follow ethics in the world of computers, right? Human cloning is unethical, but computer cloning isn't. So we can just do whatever we want, right? Why bother configuring servers and doing all those steps manually when we can just clone servers all over the world? So we can skip the education process. And that's what the AWS AMI thing I mentioned before is, which is essentially a description of what the machine looks like when it's made. And essentially it is a representation of, think of it as a Docker container for hardware, right? It's, you tell it what kind of operating system you want installed and what kind of very specifics you want to do for it. And Packer essentially is an AMI builder, in case you were wondering. Docker does this for software, right? But you also want something for hardware, and that's what you use Packer for. Step 3 in the life of a SWE freshman is getting an offer, right? For us, it's pretty hard, but if you were born for the explicit purpose for working in SWE, it's not that hard to find the offer because you were given to it when you were born, right? So that would be called container orchestration, right? When you're being told what to do. And in our concept of Kubernetes, you effectively define the projects you have to get done as a SWE freshman, and you give it the various containers it needs to run. Docker Compose is a more simplified version of what the Kubernetes sets do. And there's also HashiCorp's Nomad, which is a very specific app designed for container orchestration. And it tells it stuff along the lines of, this is what containers you need to run, what versions, and the various scaling logics for each, right? You manage what kind of containers and programs need to be run. This is the most variable part. Be creative. You can, as long as your app does what it needs to do, you can have fun with all of the parts in container orchestration as much as you can have fun in that perspective. What happened to step 2.5, joining ACM? I'm sorry, but I don't need to join ACM if I can clone myself as coming out of ACM. So you can skip that process entirely. Sorry. Anyway, step 4, when it comes to going to be a SWE freshman, is to get your laptop from IT. Right? You need to have the tools you need to work. And when it comes, because you are the person that does the work, but you need your tools to work them with. And with sorry about that. With containers, it's the same thing. You need to have the databases you need to run on. You need to have your IPs and environment variables that your backend and front end need to run properly. And that is called service discovery. Service discovery is done by Kubernetes under the form of services, where it tells various programs in certain sets what kind of services they need to run, like, for example, load balancers or other kinds of more complicated abstractions over the things I've talked about before. Consul is HashiCorp's version of service discovery. In short, it's basically where you tell each Docker container what environment variables it needs. It's definitely more complex than that, but at the core basics level, that is the most important part. Additionally, Kubernetes provides ingress here. Ingress is the concept of providing the input of the internet requests into the Kubernetes clusters, and egress is the part that puts it out. Ingress can be done like it provides load balancing, API gateways, etc. Big buzzwords that are part of Kubernetes, but in essence, service discovery is where you are also given, say, the parts that you need to access the world. In essence, this is the replacement for Caddy. And if you want a metaphor for it in real life, it's when you're given the VPN to connect to the to your workplace, right? The VPN client and the various parts you need for that. But the problem is you need VPN access. And to do that, you need to know what your credentials are for your VPN, right? You need your username and your password, and you want to keep that securely, right? And that is the process of secret management. Kubernetes is terrible at secret management by default. It is terribly insecure. It stores secrets in plain text, essentially, and it does not have many things that make secrets proper, like, for example, key rotation, which is the concept of making your keys short-lived so that no hacker could find them and potentially use them to hack your entire infrastructure because you never change them. HashiCorp's Vault is the industry standard for this. Even if you have a Kubernetes cluster, you will use this. And secret management is the process of passing secret environment variables to apps, right? Passwords, certificates, and varying other things. Like I said before, this is important for cybersecurity purposes. And most importantly, because you want to have as little chance as possible for someone to be able to take your credentials and use them elsewhere. And you want to have this step be very well solidified in your Kubernetes cluster. Step 6, working, right? You still have to work as a sweet freshman, sadly. And in this step, normally you don't have to do anything, but as a sysend, you do want to monitor your various instances. You can use tools to do this. I've mentioned Grafana before. Prometheus is the tool that takes the system resources of a node or various other kind of data points. It's a database that is specialized in handling time-based information that passes information to Grafana. Kubernetes by default has an analytics for pod performance. So thankfully, you're given the resources to check if things are going slow or fast or not. You also want to look into bin packing. Kubernetes does this by default. It's the concept of putting multiple programs in one server to fully utilize the resources it has. You want to be careful with this, though, but Kubernetes manages for you automatically. And it's still work you have to do, right? You still have to multitask when you go to school. And scaling is also managed by Kubernetes. So thankfully, you don't have to deal with that. Step 7. At some point, you might have to switch jobs, right? That would be pod reallocation. And as a simple concept, for computers, it's a lot easier to switch jobs because you don't have to get an offer. They're already given what they have to do. And that can happen if scaling occurs, right? Pods might move around and you might need to switch all of the variables and everything. You basically repeat steps 3 to 7 over and over again. And as a step 8, at some point, you'll have to retire. And that's just instance destruction, right? If you have too much hardware, you want to minimize costs. You'll want to destroy the instances that run those things so you don't pay for them. And this is just when resources are not needed. At this level, with all of this stuff, infrastructure is as ephemeral as containers. At this point, you can destroy and make servers as often as you want because at this point, you've reached a level where things vary so much that even infrastructure is as variable as Docker, right? And that's it. Thank you for coming to my workshop. Thank you for hopefully listening. And I left this section for any questions you might have about the entire workshop, and I can spend as much time as y'all want to deal with whatever questions you may have about the material. So thank you for listening, and I'll take any questions you want. You can unmute, or you can even type them in chat. So yeah. I will pause the recording.